Hello everyone, thanks for tuning in today to listen to our presentation. In this work, we unveil the 5G mid-band landscape from network deployment to performance and application QoE. My name is Rustin Fezu, and this work was done by the University of Minnesota with collaborations from IMDR Networks in Spain, the University of Southern California, and the Federal University of Para in Brazil. Commercial 5G networks is known in reality today and is constantly evolving. 5G operate in different frequencies, low band, mid band, and high band, or mmWave. Going to high frequencies are good in many ways. It opens up much more spectrums. This offers much higher bandwidth than 4G, allowing for higher data rate transmissions. But higher frequencies suffer from signal propagation issues, making them very sensitive to obstructions. Due to these physical layer issues, the coverage footprint provided by mmWave 5G is comparatively very small. For example, little is known about 5G midband. What about the 5G midband deployment landscape and configuration characteristics in the world? How do operators configure the 5G midband, and what are the trade-offs? What are some issues? The second question we look at is that can it achieve high throughputs like mmWave 5G and help support emerging 5G use cases? What are the 5G midband implications on application quality of experience or QoE? How can application developers leverage 5G midband? And lastly, how does 5G midband compare to mmWave under mobility? Why is 5G midband viewed by many as the sweet spot of 5G deployment? To answer these questions, we conduct measurements in 4 European countries across several cities and the United States. To the best of our knowledge, this is the first cross-continental 5G measurement campaign. We chose these geographical locations as a representative example of a large unified market in the United States and a fragmented market in Europe, where multiple operators typically own and manage their networks infrastructure independently within their respective European countries. In Europe, we conducted measurement studies in Madrid, Spain, Paris, France, Rome, Italy, Munich in Germany, and in the United States, we conducted measurements in Chicago. We select operators with the lion's share of mobile market. Orange and Vodafone in Spain, Orange and SFR, Société Française de Radiotéléphonie in France, Vodafone in Italy, Telecom and Vodafone in Germany, and T-Mobile, Verizon, and AT&T in the US. We built a measurement platform including 23 unique contract SIM cards, 6 smartphones, and over 100 servers, and conduct 5G measurements across these countries. Our dataset and artifacts are released at the link below. Using this dataset, we start by presenting a comparative analysis of 5G midband landscape and configuration parameters across these European countries. In Europe, the 5G midband usage and deployment is rather uniform. All operators utilize the N78 band, characterized by spectrum ranges from 3300 to 3800 MHz. As per 3GPP, channels in the N78 band multiplex the downlink and uplink data within the same frequencies, that is in TDD mode. Differences emerge in the channel bandwidth adopted by each operators, spanning from 80, 90, and 100 MHz. According to 3GPP, the 100 MHz channel is the maximum channel bandwidth allowed for midband. A key takeaway here is that the same operator may use different network settings in different countries. For example, Vodafone utilizes a 90 MHz channel in Spain and an 80 MHz channel in Italy. Taking the case for Spanish operators, Orange utilizes 100 megahertz channel and a 90 megahertz channel in Spain. We point out that this spectrum is largely as a result of what each operator can acquire in their respective countries via auctions or other means. This constitutes one of the major expenses of mobile operators. An equivalent examination of US operators' bands and channel bandwidth reveal a more diverse deployment when compared to their European counterparts. Verizon and AT&T utilizes band N77, a subset of the C-band, with channel bandwidths between 3300 and 4200 MHz. Verizon deploys a 16 MHz channel while AT&T deploys a 40 MHz channel respectively. In contrast, T-Mobile adopts a more diverse approach by deploying its 5G mid-band services across two distinct bands, N41 and N25. Within the N21 band, with frequencies between 2.4 and 3 GHz, T-Mobile leverages two channels, one with bandwidth of 100 MHz and another with 40 MHz, both configured for TDD operations. In the N25 band, which is around the 1.9 GHz, T-Mobile utilizes two pairs of channels, each with a bandwidth of 20 and 5 MHz respectively. The N25 band operates under the frequency division duplexing mode, FDD, accommodating different downlink and uplink channels. T-Mobile effectively combines these N21 and N25 channels in various permutations for carrier aggregation. Verizon and AT&T combine their mid-band channels with low-band while European operators are yet to deploy carrier aggregation. A key takeaway here is that, unlike European operators who own large contiguous channel bandwidth with smallest of 80 MHz, US operators own fragmented channels and thus foster techniques like carrier aggregation to boost data rate. As we have shown in our other SIGCOMM paper, please refer to Wei Yi and all the paper we published this year. We next quantify commercial 5G mid-band performance and configurations. Now, the second question we want to look at is, do 5G mid-band deployment configurations affect the physical layer performance and its implications on applications? This figure shows the downlink throughput of both European and US operators. We can see that Vodafone Italy outperforms all European operators, while T-Mobile performs best among US operators. A closer look at these results reveal that wider channel bandwidths do not always yield a higher throughput, contrary to Shannon's theory. For instance, Vodafone Italy owns an 80 MHz channel, the lowest among all European operators, but it's able to perform best. Another example with Vodafone and Orange Spain, both with 90 channel bandwidth, is able to outperform Orange Spain with a 100 MHz channel. Now, we zero in and conduct a deep analysis on this use case in Spain between Vodafone Spain 90, Orange Spain 90, and Orange Spain 100 MHz. We therefore ask a series of questions to answer why this performance is as such. The first question we look at is that, is it because the Vodafone UE it's allocated more resource blocks, hence performing better? And the answer here is no. In fact, we also analyze the physical resource block deployments allocated based among these three operators. And we can clearly see that the higher channel bandwidth, which is Orange Spain with 100 MHz, which is the green here, configures more resource elements, which is the green plot here, when compared to Orange Spain and Vodafone Spain. The next question we ask is that, is it because of the QoE modulation configured by these different operators? For example, one might use QoE256 while the other one might use QoE64. We analyzed the QM performance among these different operators. As we can see here, Orange Spain with 100 MHz configures QM'24 98% of the time, while Vodafone Spain and Orange Spain with both 90 MHz at least utilizes 256 QM 7.6 and 8.2% of the time. Hence, the QM cannot solely explain why these performance differences exist. We next ask the question, what about MIMO layers? In terms of the number of MIMO layers configured, we find that Orange Spain with 100 MHz configures 4x4 MIMO layers only about 13% of the time, compared to 87 and 83% of the time with Vodafone and Orange Spain, both with 90 MHz. Therefore, this performance is largely attributed to the number of MIMO layers configured. Now, the question remains, but why Vodafone Spain is able to utilize 4x4 MIMO layers more percent of the time than Orange Spain with 100 MHz? To further understand why these MIMO layer configuration differences exist between Orange and Vodafone with 90 MHz and Orange with 100 MHz channel, we conduct mobility experiments around our measurement location. As we can see on the figure on the bottom left, Vodafone's users exhibit better signal strength compared to Orange users with 100 MHz. This is attributed to denser base station deployment for Vodafone, as you can see on the figure on the bottom right, where Vodafone deploys 3 base stations around our measurement location when compared to only 2 base stations for Orange 100 MHz. This result signifies the importance of 5G midband coverage and base station deployment for 5G midband performance. We have also conducted uplink, physical throughput, and 5-layer performance. Please refer to our paper for more details. The figure on the right is a summary of the interplay among the different configuration parameters and dynamics, including the resource element allocations, the MCS, and MIMO layers on performance. This therefore begs the questions of, do 5G midband deployment configurations and dynamic parameters like MCS, MIMO layers, etc. matter for applications? This figure shows 6 representative results from video streaming experiments conducted at different times using Vodafone Italy and Orange Spain. We quantify the video streaming QoE in terms of the average normalized bitrate on the y-axis and the average stall time. We see that these 3 channels yield similar physical average throughput performance. Therefore, the normalized bitrate are closely similar. However, their stall time performance varies significantly. Therefore, we were interested to understand the channel variability and whether this has an impact. We introduced a scale variability matrix to characterize channel throughput and parameter variability. This formula essentially quantifies the cumulative data sequence variation from one point to the next based on a specific interval t. It is therefore clear that a larger Vt, the more varying the data sequence is, and a smaller Vt, the less varying the data sequence is. Please refer to the paper for more details. Using the scale variability formula, we therefore quantified the MCS and MIMO layer variability for the same operators as our video streaming experiments. The figure on the right shows the corresponding channel dynamics characterized by the variability in MCS and MIMO layers when t is equal to 150 milliseconds. We see that in general, higher 5G throughput tends to lead to higher average bitrate. On the other hand, 5G channel variability clearly influences the average stall time performance. These results suggest that developing adaptive algorithms that can better accommodate 5G channel variability, making them 5G aware, is key to enhancing application QoE. In this slide, we further try to quantify and align the throughput and channel dynamics variability with the application QoE like video quality and the client buffer level. We further zoom in into 2 locations to clearly show their impact. Please, for the sake of time, refer to the paper for more details. Now, having shown how the channel variability impacts QoE, we ask ourselves how can we leverage this insight to improve video streaming quality. We propose a simple adaptation mechanism by using smaller video chunks. We use 1 second and 4 second video chunks. And as we see on the figure on the right here, the 1 second exhibits higher bitrate and smaller stall time. Please refer to the paper for more details. The next question we looked at is that what may affect these channel variabilities? We conduct different experiments at different locations within a cell, and we see that the further away you are, the more variability a user can experience. The last question we look at is that why is 5G midband viewed by many as the sweet spot for 5G deployment? In this figure, we show the throughput and channel variabilities comparing 5G mmWave to midband across multiple time scales under mobility. Looking at walking, we see that mmWave 5G exhibits higher variability, both in terms of MCS and MIMO layers, which translates directly to higher throughput variability. Comparing driving scenarios, we see that, again, millimeter wave 5G exhibits higher variability compared to midband 5G. Next, in terms of application QoE, we compare the video streaming QoE of 5G midband and mmWave. In this figure on the left, we see that while mmWave 5G increases the achievable average bitrate overall, the bitrate QoE improvement often comes at the expense of increased stall time when compared to 5G midband. This is because 5G mmWave is far more variable than 5G midband. On the right, we see that 5G mmWave struggles to maintain good QoE performance when a user is driving compared to walking. The average stall time also degrades significantly when driving when compared to walking. This result partially substantiates the sentiment of disappointment in 5G mmWave that have been expressed in the public by many. To conclude, we have conducted the first cross-continental in-depth measurement study of 5G midband deployment in both Europe and the US. We have characterized the 5G midband performance and shown that it is a complex task. We have provided insights to operators on how to better configure and optimize the 5G midband deployment, and we have also provided pointers for application developers to build 5G aware applications. Finally, here are all the authors of this paper, and our measurements and data set can be found at the link below. Thank you.